So my topic is wasting the remote sensing with hollow microsphere. The outline include sensing principle and wasting remote sensing with hollow microspheres. And this also includes 3 points. The first one is reflective index sensing. The second one is thermal sensing. The third one is carbon dioxide gas sensing. The surroundings of the microsphere include gas, liquid, even solid. Uh, If the surrounding change will cause reflective index changing at the surface of the microsphere, so the resonance wavelength shift. However, if the surrounding not change, the curve of the microsphere is changed. It will also cause resonance wavelength shift because this uh, effective reflective index was changed. So we do some work about how to change the curve of the sphere. Uh, this this is the microscope images of hollow microspheres. We buy this from 3M company. We make a hole on the hollow microspheres. This is the SEM photo of the sphere with a hole. The diameter of the sphere is about 50 microns, and the hole is about 5 microns. We broke the hole to we broke the sphere to measure the thickness of the shell, and it's less than 1 micron. To make this hole, we first use the UV adhesive, fix the microsphere on the end face of a single model fiber. Then a copper probe with dropped HF to squeeze the microsphere. We operate this under a fusion because we can see the process clearly. The silica capillary tubing buy from the poly uh, micro technology. It has outside diameter about 162 microns and inner diameter about 100 microns. We pull the tubing with 100 flame to get a microtube with diameter down to about 5 microns. This microtube was connected with a needle of an injector by UV adhesive. Then put the injector uh, on the injection pumper. The reflective index fluid we buy from the Cali lab, and the range from 1.6 to 1.7. We inject the reflect index fluid in the hollow microspheres, and this is the injecting process. The fluid will not uh, get out from the hole because the surface tension. The, the experimental setup is like this. Liquid filled hollow microsphere is coupled to a tripped fiber. The transmission spectra were recorded. This is before the liquid field, and this is after the liquid field. The Q factor from 1.27 uh, order 5 decreased to 0.56 order 5. It's almost reduced 1 times. And the distribution of electric magnetic field is simulated by COMSOL software. The reflect index from 1.45 to 1.47. We found the resonance light change from the wall to the core. Interesting thing is near the 1.45, the resonance have a jumping point. You can see the resonance wavelength shift in one line when the index below 1.45, and in another line when the index higher than 1.45. It also means there are two sensitivities for the reflective change. It is not a linear shift, it is a two-linear shift. We also do some thermal sensing work. This is very simple. We put a heat stage in the bottom of a glass box, and we fix the hollow sphere on the top of the box because we operate under the microscope. We abandon the shift as the temperature increased. This is a blue shift. So different liquids such as alcohol and liquid crystal fell into the hollow microsphere and will have different FSR and also have different sensitivities to the temperature, because the wavelength shift is also determined by diameter of the microsphere. If the diameter change, the FSR will be different and the sensitivity to the temperature is also different. Another work is carbon dioxide sensing by microbubble. We made the microbubble by heating the silica tube with a fusion electrode, and this bubble has a diameter of about 300 to 220 microns, and it has a shell with thickness about 11 microns. We inject the pH-MB solution in the bubble and heating the bubble at 70 degrees for 3 hours. There will be a pH-MB film at the inner surface of the bubble, and this pH-MB is a polymer solution, and the chemical structure of the pH-MB is this. It can react to the carbon dioxide and will change the reflective index of the inner surface of the bubble. As the increase of the concentration carbon dioxide, you can see there is a blue shift of the resonance wavelength. It means reflective index of the bubble was decreased. We got a high sensitive about 0.4 pm every ppm, which is almost 100 times higher than the other report. So this is able all on my topics today, and thank you.